Today we're going to be reviewing this handy little eval board that allows you to do a barrel jack power replacement with USB-C. Over here you can see you've got a USB-C connection coming in, and there's an ideal diode that the voltage, if it gets turned on, will come out to the output pins of the USB-C power. Also, down here we have a PD controller, USB-C PD controller chip, which allows you to listen to the control pins coming in off the USB-C connector. We've got some dip switches over here to set up the minimum and maximum bus voltages, and also the bus. So here's your min bus voltage, max bus voltage settings, and here you can set up the max current setting that the power source has got to be able to provide in order to turn on the power from the USB-C connector through this ideal diode into the output screw terminals. So we're going to be reviewing this a little bit here, and this is what the board looks like. These buttons right here are the 4 switches that set up the current settings, and then these are for the min and max bus voltages. So what we'll do is we'll scroll down a little bit here, and here's a little bit of information associated with all these dip switches and some of the other LEDs and other headers and things of that nature with the hardware. Some more information about the pins. There are pins that can plug onto a breadboard underneath that you can take advantage of if you would like. As we can see right here, the settings for the USB current voltage will take place only at power up. So what we do is we're going to set up a current setting for our USB power source to have to meet in order for the voltage to get turned on. On this particular example, I'm going to be using this little, I think this is like a 45 watt USB-C power source that can negotiate different voltage levels and output power levels with the little breadboard. So here we can set up our max current operations needed by the power supply. Here we're setting up, this is the min and max voltage levels. So you can see there's 5 volts, 9 volts, 12 volts, 15, and 20 volts. And here's some examples of different power settings that we can get, 15 watts, 27 watts, 36 watts, and so on. So if we scroll down here, we'll eventually, this is an example of how you're hooking up your wall wart, and you got USB-C cable and negotiation going on there to this little eval board here. And we can measure off of these terminal pins what kind of voltage is coming out after power is enabled from the wall wart. So if we scroll down a little bit more, here are some wattage settings that we can get out of this particular solution. Here's one example of setting up 5 volt levels and making sure that the power source can at least deliver a half an amp. So this is how you set up the switches. What I'm going to do here is go to this example here, which is kind of interesting. We're going to have 9 volts min to 12 volts max coming in, and we want 3 amps out. So we're going to get that example running here, and you can see what it looks like here. And then after that, I don't think we're going to go and test out this example, but here you can go from 9 volts, and then here we're going to be outputting I think up to 15 volts on this one. But I'm not going to do that one in this little video, but these are just some of the other power settings that you can get out of this board. And it's got some design files and some other chips references that are used. So now we're get into looking at actually powering up the board here. Okay, so at this point we've got our switches here configured to operate at the 9 volts. Over here I've configured the current switches to put out, I think that was 3 amps. So we want to make sure that our wall wart is capable of putting out 3 amps. If we program these current switches to put out like 5 amps, then this guy will not turn on the voltage to our multimeter here. So let's go ahead and plug in the power source, the wall wart, and we'll see what happens with the supply voltage. Okay, so we're going to shut off our load here. Okay, so at this point we can see right here, this is the output voltage. We got 9 volts coming out of our ideal diodes. We also can see over here, this is saying 8.89 volts coming in, and very little current is coming through the wall wart. At this point, if we turn our power load on, we have now 3 amps being loaded down on this particular board here. Right now we have 8.48 volts coming in, and there's like 3 amps flowing from the input of the wall wart through this little test USB-C tester into this PD USB-C controller board, and then out on these terminal wires it's going up here. Actually this is going to the load over there. The load is saying 7.3 volts, but there's some voltage drop across the cable. This right here is what is truly coming out of those the green terminal pins there. So little voltage drop on this board here as the power is going through. So right now over here you can see we're pulling about 21 watts of power through this situation. What I'm going to do is I'll shut off the load, electronic load, and what I'm going to do is unplug the power. And at this point I'm going to flip some of these current switches all high, which is saying give us maximum current out of this, and this cannot deliver 5 amps at 9 volts. So when I plug in the power, at this time these LEDs will not light up, and we can see that the voltage over here and this voltage here, it's not outputting 9 volts anymore, because the wall wart cannot deliver that kind of wattage. So the PD controller is just saying can't turn me on, and we'll have to get a bigger wall wart. So at this particular time I'm going to take these dip switches and I'm going to flip them in the opposite direction, and that will say the wall wart's got to be at least larger than a 1/2 amp. So if I unplug the wall wart and then I plug it back in, the wall wart can deliver more than a 1/2 amp. So the voltage turns on the output, and we can see we got 9 volts going in there. So that's set up for the 9 voltage or 9 volt configuration. What we'll do is we'll now switch that to maybe a 5 volt configuration with these voltage switches, and then we'll see that when the power and the voltage turn on the electronic load, it will go from 9 volts down to 5 volts. Actually, I might actually jump that up to like 15 volts instead. Do something a little bit more focused around USB-C higher power scenarios. So let me shut off the power here and get some things ready. All right, so what I did is I changed the dip switches to give me about 3 amps of current, and then both the min and the max voltage levels, I set those for 15 volts. So when I applied power over here on the wall wart, the 2 LEDs turned on. I don't have the electronic load turned on yet, but as soon as I turn it on, we're going to see now we're dropping about 40 watts through this little bridge board here. And here's our output voltage, close to 15 volts here. Voltage coming in from the wall wart is about 14.5 volts, and the voltage going out is about 14.5 volts. So this little controller board is doing exactly what it should be doing, is negotiating over the USB-C interface, the CC lines, to bring in the necessary negotiated power from the wall wart, if the wall wart can deliver that amount of power being negotiated. Then everything gets turned on and the power is brought over. If not, if the wall wart cannot deliver that much power, then it never gets turned on. Anyway, pretty interesting little eval board here. So hopefully you liked the video. And this is the part number, which is a CN0581. So this is from Analog Devices. Anyway, please like the video and like, share, and subscribe. Thanks.